All right, everybody, here come the big calculations. Today we're going to look at the concept of limiting reagent or limiting reactant. I would like you to take a look at least one of the links I posted of other teachers' explanations of limiting reagent before we tackle these example problems because they work out a lot for you as well. So we've done a lot of different factor label conversions, both standalone mole calculations as well as stoichiometry problems. Now we're going to see what happens when we involve actual quantities of substances and how they interact with each other. So just as a quick review, this do now question, what is the volume? So we're looking for liters of a 12-gram sample of sulfur dioxide gas at STP. So anytime you have a gas at STP, you need to remember our magical number of 22.4 liters per mole. That could be used as our conversion factor. So to do this question, we write down what we're given, 12 grams of SO2. We write down where we're going, liters of SO2. Now, how are we going to get there? We can't go directly from grams to liters. We have to pay the mole toll, so we have to convert 12 grams of sulfur dioxide into moles using the gram formula mass of sulfur dioxide. So that is 64 grams per mole. So I'll put 1 mole SO2 on top, 64 grams SO2 on bottom, times 22.4 liters of SO2 per mole of SO2. My grams cancel out, my moles cancel out, I'm left with liters. I put in my math, which would be 12 divided by 64, and then times 22.4, which gives me a 4.2 liter sample of SO2. So that is a basic multi-step conversion problem. Next up. So now we're going to look at what happens in actual situations with chemical reactions. We usually don't have exact combinations of ingredients when we're putting together our reactions. Usually something is used up first and some stuff has elements or compounds left over. The substance that runs out first limits the amount of product that we can actually make. And that substance that limits the amount of product, the reactant that limits the amount of product we can make is called the limiting reagent or limiting reactant. It's the same thing, it just depends on who's teaching it, but it means the same thing. So here's an example. In any other video you watch with this concept, they're going to talk about some sort of recipe or putting something together to show you how ingredients run out first. So I'm talking about cheeseburgers because yum. So I want to make cheeseburgers. Each of my cheeseburgers requires 1 bun, 1 all-beef patty, and 1 slice of cheese. Now in my pile of stuff, I have 10 buns, 8 patties, and 12 slices of cheese. So with those ingredients here, and with the ratio of ingredients required for me to make a cheeseburger up here, how many actual cheeseburgers can I put together? Pause. And we're back. So how many cheeseburgers can I make? I can make 8 cheeseburgers. Why can I only make 8 cheeseburgers? Pause. What's going to run out first? My patties will run out first. Right? As soon as I put these all together in a 1-to-1-to-1 ratio, I'm going to run out of all beef patties. So I'm just going to have buns and cheese left over. So the amount of patties I have limits the amount of product or cheeseburgers I can make. Another example, I want to make double cheeseburgers because it's party time. Each of my double cheeseburgers requires a bun, 2 patties, and 3 slices of cheese, and you're probably going to need some sort of antacid. Okay, now in my ingredients pile this time I have 10 buns, 17 patties, and 15 slices of cheese. So those aren't in the right ratios to make a double cheeseburger. It's just like a random assortment. So think about how many double cheeseburgers, based on the ratios they require, am I able to make? Pause it. And we come back, and you should figure out that we can only make 5 of this type of cheeseburger because the cheese is going to run out first. Based on the amount of cheese that each double cheeseburger requires, I can, if I divide that out, 15 divided by 3, that only gives me 5 cheeseburgers. The patties won't run out first because 17 patties divided by 2 patties in each burger gives me 8.5. And my buns wouldn't run out first because 10 buns at 1 bun per burger would let me make 10 cheeseburgers. But since I'm limited by the amount of cheese I have, I can only make 5 cheeseburgers altogether. Now, let's put this into chemical reactions. These steps really don't make sense in isolation from an actual scenario, so I'm not really going to spend time going over this. But you're going to need a balanced equation, obviously, and you're going to have 2 different starting amounts, the amount of one of your reactants and the amount of another reactant. You're going to have to convert both of those into the same product. So you're going to run 2 stoichiometry problems when you're doing each of these limiting reagent problems. The reactant that gives you the smallest amount of product is going to be the one that we say is the limiting reagent. So that sounds confusing, but once we start working on these, I'm going to show you how this works. So this particular problem I have completely worked out for you. So I have a balanced chemical equation, nitrogen reacting with hydrogen to form ammonia. And remember that the coefficients in the balanced equation indicate the mole ratios in the reaction. So in my scenario, I have 10 moles of nitrogen and I have 10 moles of hydrogen. So I'm going to figure out which is the limiting reagent here. So I'm going to do 2 stoichiometry setups. I have 10 moles of nitrogen to start, which is what's given to me in my problem, and I also have 10 moles of hydrogen to start. So I'm going to run 2 parallel problems here. So first I'm going to take my nitrogen and convert it into moles of ammonia. And again, the way that I convert moles of substance A into moles of substance B is by using the coefficients from the balanced equation. So moles of nitrogen cancel out, moles of ammonia stay put, I multiply across, and I get 20 moles of ammonia. Now I'm going to do the same thing for the hydrogen using the ammonia and the hydrogen's coefficients from the balanced equation. So this math would be 10 times 2 divided by 3, which gives me approximately 6.7 moles of ammonia. So I have 2 different answers here, which means that if I'm dealing with just ammonia and an unlimited amount of hydrogen, I'd be able to make 20 moles of ammonia. Oppositely, if I had the 10 moles of hydrogen and an unlimited amount of nitrogen, I'd be able to make 6.7 moles of ammonia. So when you look at your answers from these 2 setups, the smaller answer that you get, in this case the 6.7 moles of ammonia, means that the hydrogen ran out before the nitrogen did. So over here I have this written, the 10 moles of hydrogen gave us fewer moles of product, so it limited our product. Therefore, the 10 moles of hydrogen are the limiting reagent. So it's not the ammonia that's the limiting reagent. The ammonia is the product that's being formed. The reactant or reagent that gave us that lower amount of product is the limiting reagent. So let me work one out for you start to finish. I'm actually going to do a few of these for you, and then I'll give you the answers to the others so you can try to match my work. Okay, so here, this is the same reaction. Now I have 10 grams of nitrogen and 10 grams of hydrogen, and I need to figure out the limiting reagent. So I have 2 starting points, 10 grams of nitrogen, 10 grams of hydrogen. I need to figure out which one of those is going to produce the smallest amount of ammonia, which one's going to run out first. So I'm going to do my nitrogen setup, 10 grams of nitrogen. Well, I need to ultimately turn this into moles of ammonia, which is not the unit or the substance that I need. So first I want to get to a unit that's usable, which is moles. So 1 mole of N2 is 28 grams of N2. Now I can convert moles of N2, moles of substance A, into moles of substance B using my coefficient step. So that will be 2 moles of ammonia from the equation over 1 mole of nitrogen from the equation. When I solve that, it gives me 0.71 moles of ammonia. So the math there was 10 divided by 28 times 2. The second setup I'm going to do is for the 10 grams of hydrogen that I have available to me. I'll convert that to moles first. And you see I'm always doing a number, a unit, and a substance. I'm not taking any shortcuts here because I get turned around too. Then I have to convert moles of substance A, so that's the coefficient from this up here, into moles of substance B, the ammonia. When I do this math, it'll be 10 divided by 2 times 2 divided by 3, and that gives me an answer of 3.3 moles of ammonia. Now I have two different answers, both with the same unit. The smaller answer is what I'd actually be able to produce. Why am I actually able to produce only the smaller amount? Because the ammonia is going to run, I'm sorry, not the ammonia, the nitrogen, the 10 grams of nitrogen is going to run out first. Therefore, for this question, which is the limiting reagent? The 10 grams of nitrogen are the limiting reagent because it gave us the fewest moles of product. Okay, the next example here, different equation. What volume of nitrogen monoxide can be made from 20 grams of ammonia and 60 grams of oxygen? So we're going to write down our starting points. We're going to start with 20 grams of ammonia for one of our setups and 60 grams of oxygen for the other setup. Our goal here isn't just to convert to moles of product, it's to get a specific unit of product, which is volume, and we're going to do liters. Liters of nitrogen monoxide is what our ultimate goal, unit, and substance are. Now, this doesn't say it's at STP, but we're just going to assume that because we can use our easy conversion factor that way. So our first step, we're going to do the first run here. We're going to convert grams to moles. 1 mole of ammonia has a mass of 17 grams. 17 because nitrogen is 14 and 3 hydrogens at 1 apiece. Next step is going to be my coefficient step. So I want to convert into the product, that's my goal, which is the NO. And there were 4 moles of each of those in the equation, the original ammonia and the NO. Now I need to convert into liters of NO using my 22.4 liters per mole. My other setup, I'm going to convert to moles here using the gram formula mass of oxygen. Then I have my coefficient step. This is from the equation above. So there's no guessing with this mole to mole ratio because you have the balanced equation. And then I convert that into liters. So that last step is the same. Oops. So I have both of my setups ready. Now I can do the math. So this first calculation would be 20 divided by 17 times 4 over 4, so that's 1, and then times 22.4, and that gives me 26.4 liters of NO. My second setup is going to be 60 divided by 32 times 4 divided by 5 times 22.4. That gives me 33.6 liters of nitrogen monoxide. Now going back to the original question, what volume of nitrogen monoxide can be made with those two amounts of substances? Well, since the 20 grams of ammonia only was able to produce me 26.4 liters of nitrogen monoxide versus the oxygen that was able to give me 33.6, this smaller amount, the 26.4 liters of nitrogen monoxide, is indeed the volume of nitrogen monoxide that I'm able to make with those quantities. I can't make more than my minimum amount will allow me. This next example here is the same equation with different starting amounts of the substances. I want you to try this problem doing the exact same method that I did in the prior example, and see if you can figure out what mass of water can be made from those starting amounts. So pause this, please try this out, and I'll come back in a few seconds. Okay, so for this one, I'm going to just give you the final answer to see if, because if you can match my answer, then I know you set the problem up right. So the final answer for this problem is approximately 10.1 grams of water is what's able to be made from the starting quantities of ammonia and oxygen that are given. This next example, I'm also just going to give you the answer for to see if you can match the work. So pause this video while you work out this problem. It should take you a few minutes. All right, so this ultimate question is two different things. Which one is the limiting reagent? Is the C3H6 limiting or is the NO limiting? And then what mass of C3H3N can I actually make? So for the first part of the question, which is the limiting reagent, the answer is the NO. That's the limiting reagent. The second part of the question, what mass of C3H3N can I make? That answer is approximately 24.7 grams. So hopefully you're able to match that up. The next example here, again, I'm going to give you the answer. So go ahead and try this one out, given these quantities of iron and sulfur. Okay, so for this one, the amount is approximately 11.99 grams of iron 2 sulfide that could be made. This next example is the same equation, but I'm going to work this one out for you. It's giving us a goal of making 300 grams of iron 2 sulfide. So if I have 200 grams of iron and 100 grams of sulfur, is this possible? So you might think to yourself, 200 plus 100 equals 300, so obviously I can make that. But yourself would be not so correct, probably. So let's take a look at how this works with limiting reagents, because it's not mass ratios, it's mole ratios. So for this one, I'm going to do two setups, one with the 200 grams of iron and one with the 100 grams of sulfur. I'm going to take this to grams of iron 2 sulfide. I want to see if one of these will hit 300. That's ultimately what I want to do. So I'll convert this to moles. The mole ratio is easy for this one because it's a 1-to-1 ratio of everything in the equation, so that makes the setup easy. But I'm still writing it. Don't skip the step. And then the mass of this one is about 87.85 grams per mole, FeS. Other setup, 1 mole of sulfur, 32 grams of sulfur. We have a 1-to-1 ratio of the iron 2 sulfide to the sulfur from the equation. Convert that into grams. I'm sorry. Eraser. 87.5 grams. And so I have both of my setups. My first setup, when I do the math, it would be 200 divided by 55.85. We could skip the numbers in the next one because it's all ones, times 87.85. That gives me 314.6 grams of iron 2 sulfide. My second setup, 100 divided by 32, we could skip the math for the next one because it's 1-to-1, times 87.85 gives me 274.5 grams of iron 2 sulfide. So based on this question, if my goal is to make 300 grams of iron 2 sulfide and I have a 200 gram pile of iron and a 100 gram pile of sulfur, I'm not going to be able to make 300 grams of iron 2 sulfide. I'm only going to be able to make 274.5 grams of iron 2 sulfide because my sulfur is going to run out before I'm able to hit that 300 mark of product. This next one I'm going to do for you as an example because you need to write the equation for it. So it's telling you the setup. The next couple, you're going to have to write the equation. So I have 3.45 liters nitrogen gas, et cetera, et cetera. So I need to balance the equation first. So I'm reacting nitrogen gas with hydrogen gas to form ammonia. So I'm just translating this word problem into a chemical equation. Now I need to balance this equation. So take a couple seconds to balance this. All right, so this balanced would be a 3 and a 2 there. Okay, now I have 3.45 liters of nitrogen. I have 4.85 liters of hydrogen. I want to figure out ultimately how many grams of ammonia I'm going to form. So I'm going to run this through. And again, this doesn't say it's an STP, but we're going to make that assumption. So my first step is to convert to moles. Then I will convert to moles of the other substance I'm looking for, which is ammonia, using the coefficients in the balanced equation. You see how systematic this is? There's no shortcuts to it, unfortunately, but it's so methodical. That's what I love about these problems. Also, I'm weird. And the second one, oops, I'm sorry. There's my mole to mole ratio step to get rid of the hydrogen. And then hydrogen is, I'm sorry, the ammonia is 17 grams per mole. Now when I do my math, it's 3.45 divided by 22.4 times 2 times 17, and that gives me 5.24 grams of ammonia. Next setup would be 4.85 divided by 22.4 times 2 divided by 3 times 17, which gives me 2.45 grams of ammonia. So what is the limiting reactant? Reactants are on the left side of the equation. So which one of these bad boys is going to run out first? The hydrogen is going to run out first. That is my limiting reactant. How do I know the hydrogen is going to run out first? Because it gives me fewer grams of product. How many grams of product am I able to make? The 2.45, because the hydrogen's running out first. This next example I want you to do on your own, writing and balancing the equation and solving the problem. So I will give you the answer after a few seconds, but I want you to pause it and work through this calculation. All right, for this one, identify the limiting reactant. The limiting reactant is going to be the oxygen. And then how many liters of carbon dioxide gas can be formed once you do the two stoichiometry setups? It comes to approximately 179.2 liters of carbon dioxide gas. Again, we're considering this at STP. Next example, again, I want you to write the equation, balance it, and run the math on this. Once you're finished, your answer should come out to 2.36 moles of water. And this last example I want you to try out as well. So write the equation for the problem, balance it, and then based on the amounts of hydrogen and oxygen that you're given, figure out how much water vapor you're actually able to make. The answer for this one is 33.75 grams of water. I know these are complex questions, but based on all of the examples you've done of stoichiometry problems and different types of mole conversions, it's really just taking your knowledge a step further and applying it. This is a really applicable calculation in pharmaceutical industry and any sort of manufacturing or industrial setting. I hope this was helpful. Please make sure to keep your work neat, organized, and labeled. If you do not, you're going to screw up. It happens to the best students. So see you next time. Good luck with these problems.